Alright, this is the pumpkin problem again, and we're going to try it to see, for this case, where the spring is only compressed by 41 centimeters instead of 51 centimeters like it was in this problem, we're going to see how much work was done by the non-conservative forces. Let's just go back and look at the diagram here. Our initial state is still going to be the same. Our final state is going to be almost the same. The only difference is, just make a note for part B of this problem, delta XF is equal to 0.41 meters. Okay, so that's 0.41 meters. And then we can go through and look at the free body diagrams. And so for each of these free body diagrams, if we're doing part B, then there's going to be a force to the left that's friction and or air resistance, or we could put two separate arrows to the left for each of these, and then this one's diagonally up and to the left. But we don't actually have to draw a work diagram because we're just finding the amount of work through the conservation of energy equation. So we're going to be using this equation, so we don't need to write out the work diagram. We don't need the work equation, FD cosine theta. That won't be used. Alright, so it still starts and ends at rest. It ends with no gravitational potential energy because it's at the bottom. Starts with no spring potential energy. And so this is just like our equation last time, except that we also have the work term. But otherwise, it's just like that. We do expect to get a negative value for the work because energy is being removed from the system by friction and air resistance. So now we go ahead and start putting in our more specific equation here. So we have mg h sub I plus WNC equals 1/2 k delta xf squared. And so then we can rearrange this. WNC equals 1/2 k delta xf squared minus mghi. And now we can go ahead and substitute in the values. So 1/2 times 2250 newtons per meter times 0.41 meters squared minus 10 kilograms times 9.8 meters per second squared times 3 meters. And we plug those numbers into our calculator, and you should definitely do this yourself to make sure you can get the right answer. And I got negative 104.8875, which I'm just going to round to negative 105 joules. We did everything we were supposed to. The sign came out negative, just like we thought it would. The units, we have, for example, right here, we have newtons per meter times meters squared, so that cancels, so we're left with newton meters, which is a joule. Over here, we've got kilogram times meter per second squared, so you can see that's going to be a newton. Newton from this part times meter, that's also a joule. So the units make sense. Magnitude of the answer, hard to say, but it did come out to the right side. Now we can look at the energy bar chart, and we have our energy bar chart from the last problem. And if we draw this similarly, still starting with whatever amount you picked up here, pick the same amount here. We still don't have any spring energy there. We don't end with any kinetic energy or gravitational potential energy. And we do end with some spring energy, but not as much as before. This was based on a delta X of 0.51. That's how much the spring was compressed. So instead of 0.51, now it's only compressed 0.41. And so let's just go up to, say, 3 bars. And that means this is going to be, the work is going to be negative 1. And these are just relative amounts, but we do see that this part adds up to negative 3, and this part, I'm sorry, not negative 3, positive 3, but both this part in this big circle adds up to positive 3, and this adds up to positive 3. And that's not the number of joules, that's just simply this relative scale with these little dashed lines, counting each of those as 1. And that's all there is for this problem.